Hi everyone, we are back and let's look at our chi-square test of independence. So again, aside from the variance and goodness of fit, we also have a test that we can run for chi-squared where we're looking at are variables independent or not independent. So let's go ahead and let's look at this and see if it works. So this test effectively works the same as our goodness of fit test. And we're going to compare our observed frequencies to expected frequencies. And when you're looking at data sets like this, you'll often see these tables. So what we're looking at here are 500 samples, and we're trying to classify if the sample exhibits a particular type of defect 1, 2, 3, depending on the processing route. So one question we may ask is there a correlation between the material of processes and the defect that occurs in the sample? Or another way we can kind of think about it is there a correlation between variables? And we have row variables and column variables here. So that's kind of a key thing here. So when we're looking at, and we can calculate these expected frequencies by multiplying the total number of observations for a row and the total number of observations for the column divided by the total number of observations. So we are going to have to do basically a total and a total column here. So let's go ahead and let's kind of break this out. So we're going to do a total here. I hope I can, please let me, there we go, perfect. And then we could do the same thing here where we have this and a total, and then there's an absolute total right here. So let's go ahead and let's start to build this up. So I'm going to do a new notebook. I'm going to clear all my variables. I'm going to move this here. I'm going to quit my kernel, and we are going to be able to move right as such. So let's get moving. Yes, I do really want to quit this. And now we can go through here, and we can say the total of each row. So I can do total, and we can do, actually, let's first start and grab our data set. Actually, I'm going to define my data is equal to, I'm going to do 120, 90, 40, and then comma, 110, 95, 45, oops, comma, 230, 185, 85. Shift enter here. Let's look at this data table form. Let's see what we got cooking here. Let's see. It does not like that. Here we go here we go here. Perfect. All right, so we got our values here. So I can pull out, for example, data, bracket, give me, actually just give me the first row. So I can do total of data 1. We can kind of put that value in here. So actually just go here. Total here. All right. So we can look at this, and actually I can see that that is going to be 250, 250. We can do now data 2. That's also going to be 250. And we can get the last one here, which is data 3. And that's going to be 500 samples. And then we're going to do total here. So here we go. So let's do, now we need basically, we need all of the rows and the first column. So let's do that. So it's going to be 460. And actually you can see the number of samples are actually incorrect here, because we can do, flatten, total, flatten, but we'll look at this data. It's actually 1,000 samples. So we got that there. So that's going to be 460. That's going to be 370. And then this will be here, 170. 170. So all these add to 1,000. All right. So we can look at these probabilities. So what we have to do is, like, this is this data right here, and we're going to call this right now. So observe obsdat equals dat, or data. So that's our observed data. Now to get the frequencies, we are going to have to take, multiply the total number of observations for the row. So if I'm looking at this data point right here, I'm going to look at this, and I'm going to take, and we can look at it here. We're going to multiply the total number of observations of the row, 250, and the total number of observations for the column, so 460, multiply, and then divide by the total number of observations in total here. So we can make a little matrix of that ourselves. But we can also kind of combine them and cheat a little bit here. So I can do, so actually we can make this total list equals, because we're going to have basically, so we can have like a 2 by 2. So 250 is going to be my row, which is first, then 460, and then we're going to have a 250 and a 370, and then we're going to have a 170, or actually a 500 and a 170. Let's see if this will work. Multiply that and then divide the whole thing by 1,000. So, for example, if I was to do 1, 1, then if I do 2, so let's say, and actually, when we look at the probabilities, I'm just trying to do this on the fly, we need to make sure that basically all the rows, basically sum to 1. So our chi-squared is going to be the same thing here, except we are going to go through the rows, some of the rows, and the columns. So those I and J's, we need to look at the observed and expected for effectively both of those. And our degrees of freedom will be R minus 1 and C minus 1. So rows, we have 3. Columns, we have 3. So how many degrees of freedom? So we should have 4. So let's look and try to calculate our observed values here. So let's calculate it out. So I'm going to do, for example, I'm trying to intuit right now. I want to show a couple of different ways, because we could write this a little bit more systematically, but I want to be able to do this, trying to see if you'd like to do this visually as well. So I'm trying to think if we do, so if I do 1, 1, so let's first do, because we need to do, let's do column. Actually, let's do 2. Let's sum of the rows and fix a column. So let's fix column 1. So for column 1, I need to do total list of 1. So I need to do 1 so times total list of 1, 2. So we do the total for the row, then column. So row, then column. And then we're going to divide by total flatten data. And there we go. So now I can go, and let's go ahead and keep the, so we can keep this. So now I want to go through fix the column and then some of the rows. So then I would do, if I want to, I'm going to look at my total list table form. I'm doing this very long-winded. It's just another way. I'm going to show you the way that I typically do it in just a second. But let's just enjoy ourselves and have fun. If you want to do it this total way, it's another step. So we now have to do. So I want to sum of the rows. So I now have to go to 110. Actually, I'd have to go to 250. So that'd be the second row. So now I'm going to sum over here. Here, I still 1, and then, but I wouldn't switch over here just yet. So I just go from here, I from 1 to length of total list. So that would give me my first row of measurements there. Then I would do, oh, this is an ugly one. So that gives me the first one, the first row there. 115, 15, 230. And then we'd have to go through now, and I'd have to go through J, comma, J from 1 to length total list. And let's just do this numerically. And I'm going to call this total method. And we can look and visualize this. So that's total method, table form. And oops, there seems to be, I think I made a mistake here. Let me see. Let's see here. I think we have to transpose this. I think we're okay, but we just have to flip the values. I flipped it here. Again, do not do this method. All right, that is correct. I was flipping the order. But so here's how it actually calculate, because we can read through and we can say we need to multiply the total number of observations for the row. So if I'm looking at my data, and we're going to do this effectively the same thing here. So if I want the total of a row, I'm going to do data of 1. So just like we did previously, the total of the row. So I'm going to take that and I'm going to multiply it by the total of a column, for example. So times total. And we know that the data, we're going to bring out all the rows, and let's just say the first column here. So, good. And then we're going to divide that whole thing by total of flatten of my data. And we get the value that we observed. These are the expected, essentially, values here. So I'm going to do this now for, first, I'm going to do it for all of the columns. Data. So I've got that value here. So that's going to go, I'm going to sum through the columns here because I want to create my list that way. That's why I had to transpose it last time. But you see this is a little bit more intuitive. Now I've got it for that. Now I'm going to go through my J. I can do J from 1 to length of, not Legendre, length, L-E-N-G-T-H, of data. And we can look at this table form, and we should see looks exactly the same. Good double check, a little bit more intuitive. So this is my expect val. So those are my expected values here. So now I can take my obsdat. I'm going to call this expectat. So now I can just build in those differences like we've done previously. So I'm going to do my obsdat 1 minus my expectat 1 and we're going to go through here. We're going to square it, divide by my expectat 1, and we get this value here. And I'm going to do table, and I am going to go first, and as you can see here, the first one, which one does that indicate? So I look at my dat 1. So that's my here, 2. So I'm changing effectively my rows here. So I need to go, and actually we can look at this here. If we look at our chi-squared, I need to go row first and then column. So I'm going to go through here. So I'm going to go row I, I. Then we're going to go through here, I from 1 to length of obstat. Get that. Then I'm going to do another table, table here, J. I'm going to go for length obstat. And then we're going to flatten in total. And that's going to be, finally, our chi-squared value. And if we can look up our tables, we can go ahead and see 95% chi-squared, again, only, never two-tailed. 4, we can look up that value. So that's 0.54, 9.448, I believe. Let's take a peek. So that is a very, very, very clear do not reject. Now, this is fantastic, and thank you for sticking with me in a long video. But let's go ahead and test it now and actually create this in R. And we can double check. So again, if it were in the do not, we're actually quite a big do not reject, so we should expect a large value here, or a large, excuse me, large p-value. So I'm going to do data. I'm going to make this a matrix of C. And I'm going to do 120, 90, 40. These are my observed. 0, 95, comma 45, comma 230, comma 185, 85. I'm going to close this, and then I'm going to do number column equals 3 by row equals true. And we go ahead and set this here. I'm going to do call names, name my columns, data, go to C, and then defect 1, defect 2. Oops. Hate when that happens. Defect 3, row names, data, let's see, annealed, cold rolled, and finally hot rolled. Here, data goes to as table, data, create that table. Now I can do my chi-square test. So chi-square test, and I can just set this up. So I'm going to do my chi-square test. I'm going to do my data. I'm going to do my confidence. So actually, we can just see the value here. So actually, if we look at this over here, we can just give the value as such. So you can see the rescaling, and actually we don't even need to set this up in this manner. So let's go ahead, let's run it. Oops, excuse me. And then, so chi-squared 0.86. Oh, isn't that much nicer? We did a lot of work to get that. P-value, very, very large, as we expected, because we're in do not reject. That's all she wrote. Fantastic. So, very, very roughly, that is lecture. So again, what does this mean? So we are in the do not reject. So we are in the do not reject regime for sure. And this is saying that the relationship with the defects in material treatment are not statistically significant, and there's no relationship essentially between those variables. So that's the key output effectively that we're, and the insight that we're gaining here. So we're not seeing a correlation effectively between our variables. So we'll see you all next video when we get to more correlations and ANOVA. See you then. Bye.